Okay, so Sean decided to try bungee jumping. Here was his mathematical formula of what the bungee jump would be. To find the release height, it was going to be the limit at time 0 of this equation. And we're going to look using radian mode at the graph from 0 to 10 seconds. So I just wanted to make sure that you could actually plug it into your own calculator successfully. If I was going to write it out with parentheses, you actually need an additional parenthesis around this entire numerator. And you're going to make sure that you're in radian mode. So parentheses, 8 sine of 5x, close double parentheses, divided by x plus 10. So I just want to make sure we can at least look at the graph. We're going to maybe work through the questions on the back together or alone, but I'm in radian mode. I can't just hit my 10 by 10 viewing window though, because I need to be able to see higher up on the y-axis. So in the y equals menu, I don't know, what part don't you understand of how to type in? At the end. As long as it's not in parentheses, the plus 10 is at the end. I'm going to change my window so that it's from 0 to 10 on the x-axis for seconds. And I don't know how high this is going to go. So let's go from 0 to 100. I don't know what the release height is, so it's hard for me to guess. You could do zoom fit too. So it looks like 100 was plenty. Okay, so when you graph this, if you notice, the peaks are not all at the second markings. So you don't have to be too strict on the graph itself. You know, I mean, it might be nice to find out how high it is, but if you just want this graph to kind of be like the relevant, like, it's kind of like this, right? So if you wanted to hit trace and just kind of walk along and see about where it is, I did 0 to 10 and then 0 to 100. Zoom fit, sure. All right, so is it working or no? Okay, go to window. I went from 0 to 10 and 0 to 100. Are you in radian mode? Probably zoom fit. I don't know why that would change your mode though. All right, so on the back page, we're going to answer some questions about the graph. So even if you don't want to spend a lot of time graphing, this is just kind of a quick sketch. Just do a quick sketch of what it looks like. We're going to answer questions in more detail on the back page anyway. So even if you just wanted to estimate, it kind of looks like this. Even if you don't have a scale, you know, just kind of like that. We're going to find out what those key points are on the back page. So I don't want you spending a lot of time graphing it because we don't know some of these values. Let's look at the questions they want you to answer. Find the release height. This is the limit of the function as t approaches 0. If you go in your table, second table setup, start at 0. Oh, there's an error there. See how there's an error? Right? Because I have 0 in the denominator. How can I get really close to 0? I can go to my table setup and count by like 0.001. That gets me really close to 0. Go to second table. What do you think it approaches? See how it's 49.99999? It's going to approach 50. So that, we just got that out of the table of values, but I want you to use what you know about limits. If I gave you this problem on your quest, could you evaluate it? Well, right now, maybe you couldn't. So this 10 over here is a constant function, right? So that is, the limit of that is going to be 10. What's the limit of this going to be? That's a trig form, right? 8 times the sine of 5t over t as x approaches 0 is just 5 over 1, right? What's 8 times 5? What's plus 10? So didn't you just evaluate the limit and it is 50 indeed? Because 8 times 5 is 40 plus 10 is 50. What the table is telling us is what we get analytically as well. What's the minimum height? So the minimum height on your graph is going to be that minimum point right there. So is it at 0 or 0.1? We don't know. So you're going to go to second, calculate, which is over trace. And you want to calculate the minimum. Hopefully you know how to do this on your calculator by now, but calculate the minimum. Move your cursor so that it's on the left side of your minimum. Hit enter. Move to the right side of your minimum. Hit enter. Move back to where your guess is and hit enter. I can't read that. 0.89, so 0.90, comma, 1.31. So the minimum is 1.31, the Y value. This is how many seconds it happened at, 0.9 of a second. So you're still 1.3, is this meters or feet? Meters. So you're still 1.3 meters off the ground, so hopefully your feet don't hit the ground. All right, so that is the minimum height, 1.31 meters. Find the resting height. So what's the limit as t approaches infinity? So you could either look at your table, right? So if we go in our table to like, what, 100 seconds maybe? Second table, that says 9.96, right? Let's look at the analytic limit. If we plug in infinity into the denominator here, won't the denominator blow up? Because a linear function is more powerful than a trig function, right? A trig function is 1, -1, 1, -1. A linear function is like a billion. So this approaches 0, so it's going to approach this function of 10, right? So the resting height, as it oscillates, eventually the person is going to end up at 10 meters. Right? So you could either look at your table, right? I'm showing you two different ways. Look in your table at what you think it's approaching. See, when you graph, see how this is approaching, oscillating right at 10? Well, you got to help yourself and go get one. Okay. Oh, okay. So now I want you to try this one on your own with your own calculator, but what's the total time of the first cycle of descent to ascent? So when you look at your graph, you're finding the peak, right? That starts right at 0. So you want to know what is the time to get to that first maximum. And then you also want to find how long it takes to get to the second little maximum point, because they want to know if all those maximums are equally spaced. So you're going to find the coordinate of these two lower peaks and grab the x values, because that's the time, and tell me what's the first descent, ascent, and then is the second descent, ascent equal in time? So you go to second, calculate, maximum. We want to find that maximum. So I move to the left, hit enter, move to the right, hit enter, move back to the top, hit enter. What is it, 1.55 seconds? So 1.55 seconds is the first descent to ascent. So then I'm going to go second, calculate again, maximum. Go to the left side of that second maximum point. Go to the right side. Go back to the top, hit enter. What's that? 2.81. So 1.55 to 2.81 is how many seconds? Oops. 2.81 minus 1.55 is, what'd you say it was? Oh yeah, we must have rounded just slightly differently, 1.26 or 1.27. So are those the same? Nope. Will the time for each cycle be the same? Nope, the time differs. And actually, if you kept going out, these lower peaks all are actually pretty evenly spaced because of the period of the function, but this first descent ascent is longer, just because it went further. So as they start to get oscillating, the descent and ascent time is actually pretty consistent because it's like the period of a sine function. So it would be the period of this function. So I'm done with that problem.